all of these graphs kind of have what we call the end behavior being the same. That each one of these graphs, as we go to infinity, negative infinity on the x direction, or positive infinity on the x direction, they're both going up. And then the leading coefficient here, the highest power is x squared. So we call this a degree 2. So this is what we call a degree 2 because that's the highest power. And then the coefficient on the degree 2 is positive. And so if it's positive and it's a degree 2, it's going to go up. And in fact, what this is a transformation of our parent function. Our parent function being f of x is equal to the x squared. We also call that the toolkit of functions. These are the very basic functions on which we're going to do transformations on. The second one here, it also is going up. The highest power here is a degree 6 because it's the highest power. And our number in front is also positive. Now the difference between these two and this last one here is that this is still a degree 4. And what I mean by still a degree 4 is that it's still an even degree. But notice how this coefficient on that degree 4 is negative. So instead of going up and up, it's going to go down and down. And so the degree of these are polynomials are going to matter, but also what the coefficient's going to do, because that's going to do a transformation on our graphs. So on these, notice these are degree that are odd. So this is a degree 7. And this one's a degree 3. This has a negative leading coefficient. So as x goes to negative infinity, my outputs go up. As x goes to positive infinity, my outputs go down. Whereas this has a positive degree, a positive leading coefficient, and so its degree looks like that. And this one is a transformation of the parent function x cubed. So we're going to be spending time today on parent functions. We're also going to be spending some time today on the transformations. So the first thing we're going to talk about is whether or not the graph is odd or even. We say the graph is even if we put in a negative x and my function does not change in value, and we say that it is symmetric about the y-axis. So if we see something that looks like this, f of x is equal to x squared. Well, when I put in f of negative x, this is negative x, the quantity squared, which just gives me x squared. So I know in that particular case, when I put in a negative x, I get the exact same function out. So we say that this is even. Now, I'm going to go back to the toolkit of function f of x is equal to x cubed. If I put in a negative x here, then I'm going to get negative x, the quantity cubed, which is going to give me negative x cubed. So if we say we put in a negative x, and then we get a negative of the function, then we say this is odd and is symmetric about the origin. Now what symmetry means when I have symmetry about the y-axis or the origin is if I put in a positive 1 will come out. So this is the point 1, 1. If I put in a negative 1, I have symmetry across the y-axis and a negative 1, but a positive 1 comes out. So we notice that this point right here has a mirror image over on this side across the y-axis. This point will have a mirror image across on the y-axis, and this point also will have a mirror image, and it doesn't matter which way I go. What I do know is I have a mirror image across the y-axis, and that's what we mean by symmetric with respect to the y-axis. Now if I look at my parent function, which is a cubed function, this I put in 1 and 1 comes out. So positive 1 comes out. So this is point 1, 1. But if I put in a -1, a -1 comes out. So we have symmetry across the origin. So what happens here must have the symmetry across the origin here. So if I have this point, then across the origin I must have this point. So we have symmetry across the origin. It's almost like 180 degrees across the origin is where the other point would be. So if I would have had a graph that looks like this, then I also have symmetry across the origin because this point relates poorly drawn to this point. This point relates to this point. And so across the origin, so it's almost like going 180 degrees across the origin is where those points are going to be. Not drawn well. That should go to the other one. This one and this one should go together. Across the origin. In your mind, it went through the origin there. So when we talk about symmetry and we talk about odd and even, it's an even function so that when I put in a negative everywhere, it's going to be not going to be changing anything at all. It's going to be an odd function as if every single sign changes. Now these are my parent functions, but if I deviate from my parent functions, in other words, I change them slightly. So if I said f of x is equal to x squared plus x plus 1, that's not necessarily going to have symmetry just because it's an even function, or just because the highest power is even. So if I go to check it, f of negative x, this gives me negative x squared plus negative x plus 1. This becomes positive x squared. This is a negative, and this is plus 1. So this is neither odd nor even because this sign stayed the same, but this sign didn't change. This side stayed the same because I have all of the signs didn't change. All of the signs didn't stay the same. This is a neither. So just because my power is 2, my highest power, the degree of my polynomial is 2, that doesn't mean that that is going to be an even or odd powered function. So what kind of questions do you have for me before you have you work on these down here? If there's no questions, then I'm going to ask you which one of these would you like me to do, and then you all are going to do the other two. B? Okay, so for B, what I'm going to do is I'm going to check it by putting in g of negative x. Whenever I see x, I'm going to replace it with a negative x. And so I end up with a negative x minus 1 over x. And my rule is, for this to be even, all my signs had to change. Well, I went from a positive to a negative. I went from a positive to a negative. So my signs did not remain the same, so this is not even. My rule is, for it to be odd, then every sign has to change, and this one is one in which every sign did change. So this function is odd. What kind of questions do you have for me? Okay. Okay, it looks like we've got some answers in, so let's go ahead and check them. So I'm going to put in for A, I'm going to put in a negative x, so f of negative x is equal to negative 7, negative x, the quantity squared, plus 1. Because I have a negative squared, it's going to be a positive x, so this just is negative 7x plus 1, negative 7x squared plus 1. So I went from a negative and I stayed negative. I went from a positive and I stayed positive. And because none of the signs changed, then A is even. This is an even function. What kind of questions do you have for me on that one? So let's take a look at C. With C, we're going to do the same thing. We're going to put in a negative x. So h of negative x is equal to negative x, the quantity cubed, plus negative x, the quantity squared, had with Desmos yesterday is we were playing around with quadratics. And so we noticed with our quadratic, when we had a plus k, it moved it up or down. So a plus k means that I'm going to go up, and if I have a minus k, I'm going to go down. So what we had, our parent function, or our toolkit of functions, f of x, was equal to x squared. So that was our original function. And all f of x equals x squared is going to go through this point, which is 0, 0. It's going to go through this point, which is 1, 1. And it's also going to go through this point, which is negative 1, 1. So this is where my symmetry across the y-axis is happening. But this is my parent function. And then what we did yesterday when we were working with Desmos is we did f of x. Actually, let me do this in a different color. We did something like g of x is equal to x squared, and then we moved it up or we moved it down. So notice that that plus 2 is not within the squared part. So that plus 2 is this k right here. So that plus 2 is that movement up or down. So I'm going to give you all a moment to use this time to draw yourself a parent function of some sort. I gave you the x squared if you want to use that. And then what the vertical shift would look like. So give yourself a moment to determine a parent function that you like. X squared is a nice parent function. And then draw where it would be with a transformation and the function that would match that. So for my example, my parent function that I chose was the x squared. And then if I had the x squared plus 2, what that would do is I'd move my y value up by 2. So this will go up to the point 0, 2. And then this point and this point will also go up 2. So this is what my shifted, not drawn well, graph would look like. So I want you to do your own parent function, and whichever one you like, and then do some sort of transformation and write down the equation for that transformation. I'll give you a moment. So say you decided that you like the parent function of the square root. So here's my parent function of the square root. Actually, do this. Move this up slightly. The square root function, so f of x is equal to the square root of x. And it's going to look like this. It's going to go through 0, 0. It's going to go through the point 1, 1. It's going to go through the point 4, 2. So that's the parent function maybe you all decided that you liked. And then your new function, g of x, would be the square root of x. And say you went down to 3. So what that does is it changes all of my y values. It doesn't change my inputs, it doesn't change my domains. It changes all my y values by taking and subtracting 3. Now this point, the original point was 0, 0. Another point that was on there was 1, 1. And another point that I chose, which was 4, 2. So by doing a subtract 3, I take my y values and I subtract 3 from it. So that point goes from 0, 0 to 0, negative 3. This goes from 1, 1 to 1, and I'm going to take 3 from that, and so I get negative 2. And then, of course, I have 4, and then I take and subtract 3 from 2, so I get negative 1. So this point is going to go down here, this point will go down here, and this point will go down here. And so that's what my graph is going to look like. That is my transformed graph. Notice that my y values are the ones that are changing. They are outside of my function, and that is the vertical translation down. Notice, just like yesterday when we were playing with the Desmos, when I had a plus 2, I went up, and when I had a negative 3, I went down. What kind of questions do you have for me? So if you have no questions, and please stop me if you do have questions, we're going to go to the horizontal shift. Now again, I'm going to choose the parent function of x squared. So here is my x squared. So here's my function, f of x is equal to x squared. And it goes through the point 0, 0. It goes through the point 1, 1. Goes through the point negative 1, 1. And suppose my transformation, because we were using these yesterday, suppose I said my g of x is equal to x plus 2, the quantity squared. So what that did is it took all of my x's, so this is changing my range, or my domain, it took all of my x's, so I'm going to do negative 1, 1, I'm going to do 0, 0, I'm going to do 1, 1. And it takes all of my x's, and what it does is it does the opposite of what's here. So I'm always going to be adding or subtracting the opposite. So I take all my x's, that's a plus 2. So I'm really subtracting off 2, so it's x minus 2. And so I've got negative 1 goes to, since I'm subtracting 2 from, goes to negative 3, comma 1. 0 goes to negative 2, comma 0. And 1 goes to negative 1, comma 0. So it's changed all of my x's. So here is where my 0, 0 went to. I'm going to go through the point, and that should be 1. Change that to 1. 1. And so I'm going to go through the point on my transformed graph. I'm going to go through the point 1, 1, or negative 1, 1, negative 3, 1. And so here's what my transformed graph looks like. So there's my g of x. So what I'd like you all to do is choose a function and then do the transformation of that. And I'll give you a moment to do that. All right, so maybe you chose your parent function, your example, to be f of x is being the absolute value of x. So here's what your original function looks like. It goes through 0, 0, it goes through 1, 1, 2, 1, 3, 1, 1, 1, 2, 2, 3, 3, 4, 4, negative 1, 1, negative 2, 2, negative 3, 3. So here's your original function. So I'm just going to choose some points. Let's choose the point negative 2, 2. Let's choose 0, 0, and let's choose 2, 2. Now suppose you wanted your g function to be the absolute value of x minus 3. So what this does, again, it is the opposite of what we want. We think we want to subtract 3, is we're going to add 3 to all of my x's. So this is going to be, so it's going to be x plus 3. And so it's going to go, the negative 2, 2 is going to go to the point 1, comma 2. And a 0 is going to go to 3, comma 0. And this one's going to go to 5, comma 2. So I'm going to go to 1, comma 2. So 1, 2, 3, 0, and then 5, 2. And so this is where my transformed graph will look like. What kind of questions do you have for me? Well, let's take a look at when let's take a look at this. So the question is, why am I going with the horizontal? Why am I doing the opposite? Suppose I have x, I'll do x squared minus 2, or I'll do minus 4 is equal to 0. And when I have x minus 4 is equal to 0, then I know this is going to factor in the difference of squares. And so what I end up with is x is equal to a positive 2 and x is equal to a negative 2. So those are my solutions. The positive 2 came from here, and the negative 2 came from here. See, notice how they were the opposite signs? If I were to graph this, I know that this negative 4, what I've learned so far, is this is a shift down of my parent function. So my parent function is going to go from 0, 0 to negative 0, negative 4. I'm going to get these two x-intercepts. here at negative 2, 0, and here at 2, 0. So when I do that solving, when I solve for x minus 2 is equal to 0, I get a positive 2. When I get x plus 2, I get negative 2. So I know that that is a movement down, and it does exactly what I expect it to do. But if I were asked to graph this, x minus 2, the quantity squared, is equal to 0, then I can take the square root of both sides. So I take the square root of both sides, and the square root of plus and minus the square root of 0 is just 0, so that didn't change anything. So I get x minus 2 is equal to 0, but x equals 2 is where it's crossing or touching the x-axis. I got a leg, so give me a moment for it to catch up. So I'm going to just put this on pause. So I end up with x is equal to 2. So when I graph this, that my 0, 0, which would have been there, actually moved to a positive 2. And so my function ends up moving to the right instead of to the left, because when I solve it, it does the opposite. Does that make sense? So if it's inside the function, it does the exact opposite of what you would like it to do. Okay. So when we are trying to graph this, let me erase this. When we're trying to graph these, what we want to do is we want to identify each one of the shifts, whether it's horizontal or vertical. So if it's outside the parent function notation, then it is going to be a vertical shrink or vertical movement up or down. If it's inside the square root, if it's inside the absolute value, it's inside the squared or the cubed or the cube root, then what it does is it goes left or right, and it always is the exact opposite of what you want it to do. Now when you're doing these transformation, order doesn't matter because you're going to get the same answer, but order does matter because it's easier in a certain order when we do the transformations. So let's continue because we still have a couple of more transformations here. Our next one is a reflection. Now we just did the reflection. We talked about odd and even functions. Here we're going to talk about a reflection. So if I have a negative on the outside of my original function, then what that does is it does a vertical reflection across the across the x-axis. So let's go back to f of x is equal to the square root of x. And then, so we know what this looks like. Oops, I want to go with this. That's not what I wanted to do. Here we go. Here's my f of x is equal to the square root of x. Looks something like that. Now if I have g of x is equal to negative square root of x, what that does is it takes all of my y's, all of my outputs, and multiplies by a negative number, and so it does a reflection across the x-axis. So that's what g of x looks like. Now if it's inside the function, then it reflects across the y-axis. So it's going to go across the y-axis. So again, I'm going to use the square root function. But my h of x is going to be equal to the square root of negative x. Now remember, everything has to be a positive number to take square root. So the only values I can put in on this are negative. And so that's what h of x does. So if it's inside the function, it does a reflection across the y-axis. If it's outside the function, it does a reflection across the x-axis. What kind of questions do you have for me? If there's no questions, here's how you would do the reflections. So if it's outside the function, then you multiply all of your vertical or your x values or your outputs by a negative number, -1, and it should be reflected across the x-axis. If it's inside the function, you multiply all of your inputs or your domain by a -1, and it should reflect it across the y-axis. The last couple of things we're going to do today are vertical shrinks and stretches, or compressions as they're called. So we're going to start with the vertical compression. Now with the vertical compression, what it means is that it's going to do exactly what we want it to do. So if we see a number outside of the function, it's going to take all of the y values and multiply them by that. And there's no weirdness, it's just multiplying it by that. So if I'm going to choose the parent function of, say, let's go to the absolute value again. So if my f of x is equal to the absolute value of x, and my g of x is going to be equal to 3 times the absolute value of x. Now remember, here's my absolute value. It's going to go through 1, 1, 2, 2, 3, 3, 4, 4, etc. -1, 1, -2, 2, -3, etc. So there's my g. There's my original function. So I'm going to choose some points again. I'm going to choose the point -2, 2. I'm going to choose the point 0, 0. I'm going to choose the point 2, 2. I could have chose any of the ones that are on that graph. These are just nicer numbers rather than the 1, 1. What that 3 does is it takes and multiplies all my y values by 3. So it's 3 times my y values. So the -2, the 0, and the 2 does not change. But what does change is all my y's are going to be multiplied by 3. So this goes to 6, 0, and 6. Because those are all my y values. So that means 0, 0 stays the same. But 2 goes to 6, 2, 4, 6. And -2 goes to 6. And so it's going to look like this. If I'm still going to use the absolute value function, if I would have had h of x is equal to 1/2 the absolute value of x. So again, I'm going to use the points -2, 2, 0, 0, 2, 2. Then it takes all of my y values and multiplies them by 1/2. So it's 1/2 of y. So the -2, the 0, and the 2 do not change. But my y values are half of what they were. So 2 times 1/2 is 1. 0 is not going to change. And then 2 times 1/2 is also 1. So again, I'm going to draw my original function. So here's my f of x function. Going through 1, 1, 2, 2, 3, 3. And in the negative. My h function is going to go through the point 2, 1, -2, 1. Still going through 0, 0. So this is half as tall as what I had before. So I'm going to stop, give you a moment, maybe do your own, maybe draw what it would look like, maybe do the equation. So I'm going to give you a moment, and then also so you can ask me any kind of question. So let's go ahead and move on to the last one, which is a horizontal. But here's a wrap up on how to graph with a vertical stretch. First, you need to identify what the vertical stretch or shrink is going to be. And you just multiply all of your y values by that number. If it's negative, it's going to just multiply by a negative number, and it's just going to do that reflection at the same time that you are doing the multiplication. The next thing and the last thing we're going to do is the horizontal stretches and compressions. So when it is inside of the function, notice that is inside of the function notation, then it is messing with your domain. When it messes with your domain, it does the exact opposite of what you would like it to do. So if it's a 3, instead of multiplying all your x's by 3, you're actually multiplying all your x's by the reciprocal of 3. In other words, you're multiplying them by 1/3. So you're dividing them by 3. We want to multiply by 3. We're actually dividing by 3. So if it's inside the function, it's going to mess with your domain. If it's a negative, it does a reflection across the y-axis at the same time that it is shrinking, or it is compressing, as they say, or stretching it. So it's a shrink or stretch, and it does the exact opposite. Now, with this one, I'm going to do it slightly different. I'm going to do the sine wave, which you all don't need to know the sine wave yet, but it will be something that you're going to learn in Pre-Calc 2. The reason I do the sine wave is because it is very, very clear on what's happening with the shrink or stretch. So if I say f of x is equal to the sine of x, then this is what it looks like. And some of you might have seen this in your previous math courses. So it's going to go through the point 0, 0. It's going to go through the point pi over 2. Actually, you know what? I'm going to do it. I'm going to just move this over so it makes it easier for me to graph this. So there we go. It's going to go through 0, 0. It's going to go through the point pi over 2, 1. It's going to go through pi, 0. It's going to go through 3 pi over 2, 1. It's going to go through 2 pi. So this is what the sine wave looks like. So there's the sine wave. My inputs were 0, 0, and I'm just going to use pi, comma, 0, and 2 pi, comma, 0. So those are my inputs. So if I say, okay, my g function is the sine of 2x, then what happens to all of these points is all of the x's get divided by 2. When all the x's get divided by 2, it is going to shrink my graph by half of what it started out with. And so what my sine wave would look like that with a shrink. If I would have said g of x is equal to the sine of 1/3 x, it actually stretches it by a factor of 3 because it's the exact opposite of what we want. And so I would have a graph that looks like this. And instead of starting at, actually I would have gone further than that out. It's just, give me a moment. It's a little bit further over before it comes out. It's going to look something like that because it's going to take those those x values and multiply them by the reciprocal. The reciprocal of 1/3 is 3. So if it's inside the function, it's going to do a exact opposite of what you want in the horizontal direction. So I'm just going to do a wrap up here because I know that we're almost out of time. I'm not going to be able to finish this today. So when you are looking at your function f of x is equal to some function, we'll call it x squared. Then g of x is going to be equal to, I'm going to have some a value out front as a multiplier. Your function, then you're going to have some b value, x minus some c value, plus some d value. Now, a and d change the range exactly like we expect. But b and c change the domain the opposite of what we expect. So this is the way I think of it. This is how I explain the whole domain range. What do I expect? What's going to happen? And all of that is if I am looking at my function and it's inside the function, and I think of this as when you're going to look at a pet and you want to bring it home from, I don't know, the pound, or what do they call it when where the pets are, Humane Society. You're going to the Humane Society to get yourself a pet. Not that this has happened to me, but this has happened to me. And I thought, oh my God, I love this dog, or my husband loves this cat. They're just exactly what we're looking for. They're outside of our house. They're outside of our function. We bring them home and they do the exact opposite of what we expected them to do. So they're now in our house. Another way I always tell my students is when you're starting to date someone, and when you're dating someone, they are outside of your house. They're not living with you. So they do exactly what you expect them to do. They say they're going to call you, they're going to call you. They say they're going to pick up their socks, they're going to pick up their socks. So they do exactly what you want because they're not in your house. They're not in your domain yet. They're outside. They're out on the range. They want to be in your domain, but they're doing exactly what you expect them to do. The moment you let them into your house, they do the exact opposite of what you want them to do. The moment they live with you, the moment you marry them, they stop picking up their socks. They stop calling you when they say they're going to call you. Not that I've experienced this or anything, but the moment they're in your house, they do exact opposite of what you want. So if they're in your domain, they mess with your domain and they do the opposite of what you want. If they're outside of your domain, they're in your range, they're in your backyard, they do exactly what you want them to do. So that's how we're going to look at this. Is it inside my function? Is it inside my house? Or is it outside of my house? So we're going to pick this up tomorrow. We're going to do some more of the transformations of graphs because these are terribly, terribly important. And otherwise, you all have a great afternoon, the rest of your morning. Hopefully this will burn off and have a nice day. And we will see you all tomorrow.